Hello YouTube and welcome back. I am Benjamin Williams and today we're going to be doing another lab within Boson NetSim. Today's lab is going to be on implementing route selection. So let's go ahead and read our objective for this lab. It says, routers choose the best path to a destination by using a number of different methods, such as administrative distance, AD, and routing protocol metrics. The level of trustworthiness that is assigned to a specific path on a router is known as AD. For example, by default, static routes to a given destination are assigned an AD of 1 and are thus considered more trustworthy than routes that are learned dynamically. Dynamically learned routes typically have a higher AD depending on the routing protocol configured. It says, if a router knows two paths to the same destination, and those paths were generated by using the same dynamic routing protocol, the router relies on other values such as bandwidth or hop count to calculate the best path. These secondary values are known as metrics. Each routing protocol uses a different metric or set of metrics to calculate the best path to a destination network. It says in this lab, you will influence route selection by using AD and by manually configuring open shortest path first version 2 OSPF v2 metrics. All right, so this is the lab topology that we're working with for this lab. We can see that we have router 1, router 2, router 3, router 4, and router 5. So we have 5 routers and they're interconnected by different links. We can see we have some Ethernet links. We have a serial point-to-point link. And then we can see that each router, except for router 1, has a local area network. So router 2 has a VLAN 100 network. Router 3 has a VLAN 200 network. Router 4 has a VLAN 300 network. And router 5 has a VLAN 400 network. So that is our lab topology that we're going to be working with. And we would definitely refer back to this as needed throughout the lab. Let's go ahead and take a look at the commands that we're going to be using for this lab. We have configure terminal, which enters global configuration mode from privilege exec mode. We have enable, which enters privilege exec mode. We have end, which ends in exits configuration mode. We have exit, which exits one level in the menu structure. We have show running config, which displays the active configuration file. We have interface type number, which changes from global configuration mode to interface configuration mode. We have IP OSPF cost, and we enter the cost. This changes the default OSPF cost for an interface. We have IP route prefix, and then we'll put the mask, and then we'll put either the next top IP address or the exit interface, and we can also include the distance. And this establishes a static route. We have show IP route, which displays the IPv4 routing table. And we have trace route IP address. This displays a hop by hop path through an IP network. So moving along, we see our IP address table, which displays all of our device names, all of their interfaces, their IP addresses for each interface, and the subnet mask for each interface. So we would definitely refer back to this table as needed throughout the lab as well. Okay, so let's go ahead and hop into our lab. We're going to keep our lab topology up in the top left. We're going to be doing our lab readings in the top right. So let's go ahead and get down to that. And we're going to be doing all of our lab configuration down here at the bottom. Okay, so let's go ahead and start with task number 1. It says influence route selection by using AD or administrative distance. It says in this task, you will influence route selection by using AD. All steps in this task should be performed on router 4. So let me go ahead and pull up router 2, router 3, router 4, and router 5. And we want to do our configuration right here on router 4. Okay, looks good. All right, so number 1, it says allow time for the network to converge. Issue the necessary command to display the routing table. How many OSPF paths has router 4 inserted into the network? Okay, so let's do an enable to go into privilege exec mode, and let's do a show IP route to view the routing table. And if we take a look at router 4's routing table, we can see that we have this route right here, which has 2 paths. So we can count this as 2 paths. So this is 2 because we can see that it's going to load balance over both of these next hop IP addresses. So that's 2 of them. We have another one right here. So that's 3. and 4 because it's going to load balance over both of these IP addresses as well. So that's 4. We have 5 and 6, and we have to count both of these because it's going to load balance over both of these IP addresses. So that's 6. And then we have 7 right here. We have 8. All right. We have 9. All right. And we have 10, 11, 12 right here, and then 13. So we have 13 different OSPF paths that were inserted into router 4's routing table. Let's see what Boson is going to say. If we take a look, it says, based on the output, you can determine that router 4 has learned 13 OSPF paths to other networks. So yes, and then it kind of just explains right here the different connections through the different routers and how those connections are interconnected. Okay, so we just wanted to answer the question. It says how many paths has router 4 inserted into the network, and we said 13, and that was correct. So let's go and move on to number 2. It says which paths to which network are load balanced by OSPF. Okay, so let's go ahead and answer that. We can see that the 203.0.113.0/30 network is going to be load balanced, and we can tell this because we have 2 paths with 2 next hop IP addresses. Both of these paths have the same administrative distance, and they both have the same metric of 65. And so OSPF is going to load balance this network over both of these IP addresses. So that's one. So 203.0.113.0/30 will be load balanced. We can also see that 203.0.113.12/30 will also be load balanced because it has an administrative distance of 110 and a metric of 2 for both of these for this network, and both of these IP addresses, these next hop IP addresses, are included in the routing table. And we can also see that this path right here to 203.0.113.24/30 will also be load balanced over OSPF. And we can see the next hop IP addresses included in our IP routing table as well. Both of these paths have an administrative distance of 110, and they have a metric of 2. All right. And the next question it asks, which paths to the 203.0.113.0/30 have the same AD and cost? So if we take a look at 203.0.113.0/30, that is this network right here within our routing table. And it says which path to 203.0.113.0/30 have the same AD and cost. Well, we can see that the 203.0.113.5 and 203.0.113.9 both have the same administrative distance of 110, and that is OSPF. And they both have the same metric of 65, which is the metric, okay? And that is the cost as well. So let's see what Boson is going to say. It says, let's go down. It says right here, one OSPF record displays 2 different paths to 203.0.113.0/30 network. A path through gigabit 01 interface and a path through gigabit Ethernet 02 interface. The IP addresses appear in the next row of output is the address that is assigned to the neighbor that is directly connected to the specified interface. For example, the IP address of 203.0.113.5 is assigned to router 1's gigabit Ethernet 01 interface, which is directly connected to router 4's gigabit 01 interface. It says right here, the first value in the bracket, which is 110, is OSPF administrative distance. By default, OSPF has an administrative distance of 110. The path to 203.0.113.0/30 is inserted as an OSPF path because no other path to this destination has a more trustworthy AD than OSPF. The lower the AD value, the more trustworthy the path. In addition, no single OSPF path has a lower cost than the 2 inserted paths. The second value, which is 65 for each path, is the calculated cost of the paths from the source to the destination. Okay? So yes, that is exactly what we just explained. So number 3, it says trace the path to router 1's serial 00 interface, which has an IP address of 203.0.113.1. And it asks what path does the router take? So we're going to be using this route right here within our routing table because 203.0.113.1 falls into 203.0.113.0/30 network. Okay, so we're going to either be taking the path to 203.0.113.5 or 203.0.113.9. So let's see which path router 4 ends up taking. So let's do a trace route to 203.0.113.1. And you can see that we took the 203.0.113.9 path. So that is this one right here. And then we got to our last hop, which was to router 1, which has an IP address of 203.0.113.1. So it could have took either this path, which it did, or it could have took this path to 203.0.113.5. But the router decided to take this one right here, which is 203.0.113.9 as the first hop. Okay, so on number 4, it says from router 4, what is the shortest path to router 1 serial 00 interface, which has an IP address of 203.0.113.1 that does not traverse a gigabit Ethernet link? So if we take a look at our lab topology, we can see if we're looking at router 4, which is right here, we can see that it's taking, it could either take the path to router 1, which is a gigabit Ethernet link, or it could take the path to router 2. But it is asking if these two links, so the link to router 1 or the link to router 2 was to be severed, or these links were to be shut down in any way, what will be the best path to get to router 1? So if we take a look at this topology, the best path will be through router 3 and then up to router 1. If we go to router 4 to router 5 to router 2 and then all the way to router 1, this would have a higher cost, and that is because of this serial link. We would have to traverse this slow serial link, and that would, as a result, cause us to have a higher cost for this network traversal. So the best path, if we were not able to go straight to router 1 or straight to router 2, the best path will be through router 3. All right, so let's see what Boson is going to say. It says the shortest path from router 4 to router 1 serial 00 interface that does not rely on the gigabit Ethernet link is the path through router 3. And that is exactly what I just said. It says router 4 is connected to router 3 by using a fast Ethernet link. Similarly, router 3 is connected to router 1 by using a fast Ethernet link. Therefore, to remove the gigabit links from the 203.0.113.0/30 paths inserted into the routing table, you should modify the AD or cost of the path through router 4's fast Ethernet 1.1 interface to router 3. So yes, that is exactly what I just explained. So on number 5, it says, what is one way in which you could use AD to ensure that router 4 always uses the path through router 3 to communicate with interfaces that reside on the 203.0.113.0/30 network? Well, if we're using administrative distance, the only way that we can modify the path to router 3 to communicate with the 203.0.113.0/30 network, which resides on router 1, is to configure a static route on router 4 to router 3, which will go to router 1. As we know, static routes have an administrative distance of 1, which is more trustworthy than a OSPF learned route. So if we configure a static route on router 4 to router 3, router 4 would then use that static route instead of the OSPF route. So let's see what Boson is going to say. It says, one means of influencing the path router 4 takes to router 1 serial 00 interface, which is 203.0.113.1, is by configuring a static route to the 203.0.113.0/30 network through router 3. By default, manually configured routes are more trustworthy than routes learned by dynamic routing protocols. And that is exactly what I just explained. It says by manually configuring a path through router 3, you force router 4 to never use the gigabit Ethernet interface or the fast Ethernet 1.0 interface to communicate with interfaces that reside on the 203.0.113.0/30 network. Okay. So number 6, it says configure a static route to 203.0.113.0/30 network through the next hop IP address of 203.0.113.17 on router 3. All right, so on router 4, let's go ahead and configure this static route. Let's do a configure terminal to go into global configuration mode, and let's do an IP route to 203.0.113.0. We want to give a slash 30-bit subnet mask. So let's do 255.255.255.252. And the next top IP address is going to be 203.0.113.17. And let's go ahead and enter there to configure that static route. Now, number 7, it says issue the necessary command to display the routing table. How many paths to the 203.0.113.0/30 network now exist in the routing table? What administrative distance and metric are reported for these paths? So on router 4, let's do a N. Let's do a show IP route to view the routing table. And if we take a look at the routing table, we can see that the first entry right here is the path to 203.0.113.0/30. And we can see that it is only one path now because that OSPF route is now gone because we configured a more trustworthy route, which is a static route. We confirmed the trustworthiness by looking at the administrative distance of a 1 right here in the routing table. As we know, OSPF has a administrative distance of 110. A static route has an administrative distance of a 1, so it is more trustworthy than OSPF. And we can see that the metric is 0 for this static route, okay? So we just answered these questions for number 7. So on number 8, it says remove the static route to the 203.0.113.0/30 network and replace it with the same route that uses an administrative distance of a 111. Will the route be more trustworthy or less trustworthy than the OSPF path? So if we configure basically this is going to be a floating static route with an administrative distance of a 111, it is going to be less trustworthy than OSPF because we can see that OSPF has an administrative distance of 110. So this route is going to be chosen, the OSPF route is going to be chosen instead of the static route because we're configuring a floating static route with an administrative distance of 111. So let's go ahead and confirm that. Let's do a configure terminal, and let's do a no IP route to 203.0.113.0. We want to do a slash 30-bit subnet mask, so 255.255.255.252, and a next hop of 203.0.113.17. So we want to remove that, and now we want to reconfigure it with a floating static route of IP route of 203.0.113.0 slash 30-bit subnet mask, so 255.255.255.252. And we want to do a next hop of 203.0.113.17. And this time we want to specify right here the distance metric for this route. So we want to put in 111. All right, and hit enter there. So now, number 9 says issue the necessary command to display the routing table. What path to the 203.0.113.0/30 network exists in the routing table and why? So the OSPF path should now be back in the routing table, but let's confirm. Let's do an N and let's do a show IP route. And now we see the OSPF path is back. And that is because we configured a static route with an administrative distance that is less trustworthy, which has an administrative distance of 111. And the OSPF path has an administrative distance of a 110. So that is more trustworthy. So that OSPF path is back, okay? So on number 10, it says replace the static route to the 203.0.113.0/30 network with the same route that uses the default administrative distance for static routes. So now we want to go back to the original static route. So let's go ahead and do that. Let's do a configure terminal. All right, and let's do a no IP route to 203.0.113.0, 255.255.255.252, and we want to do 111. Oh, excuse me. We want to do 203. I got to do the next hop. 203.0.113.17. And then we want to do 111. To remove that, let's do an IP route to 203.0.113.0, 255.255.255.252. We want to do 203.0.113.17 as the next hop and hit enter there. So now we're back with the default administrative distance for the static route. So now it says trace the path to 203.0.113.0/30 network. It says what path does router 4 take to router 1 serial 00 interface, which is 203.0.113.1 now. So it should use this next hop IP address of 203.0.113.17. So let's confirm that. Let's do a N, and let's do a trace route to 203.0.113.1. And yes, we use this IP address of 203.0.113.17 as our first hop because we configured this static IP address or this static route to this network, and it is more trustworthy than OSPF, okay? So now on number 12, it says issue the necessary command to display the routing table. How many routes to the 203.0.113.0/30 remain in the routing table now? So we should only have one path to that network, and that should be the static route. So let's do a show IP route, And yes, we can see right here at the top of our routing table, to the 203.0.113.0/30 network, we have one route or one entry, and the next hop is 203.0.113.17. Okay, so that is the end of task 1. Let's go ahead and move on to task number 2. It says influence route selection by using OSPF metric. It says in this task you will influence route selection by examining and modifying OSPF cost values. So number 1, it says on router 5, issue the necessary command to display the routing table. How many paths to the 203.0.113.8/30 network has router 5 inserted? Why did the router choose these paths? So let's go to router 5. Let's do an enable. Let's do a show IP route to display the routing table. Show IP route. And we want to specifically look for the 203.0.113.8/30. So that is this entry right here. And we can see it has 2 entries because of the administrative distance of 110. And the metric for both of these next hop IP addresses is 2. So it said, why did the router choose these paths? Well, apparently that is the most trustworthy path, or these 2 entries right here is the most trustworthy entries that we have inside of this router. So that is why these 2 are chosen. They both have the same administrative distance and they both have the same metric. So as a result, that is the only way this router knows how to get to this network. Okay. So number 2, it said, how does OSPF calculate the cost of a path from source to a destination? Well, we know OSPF does its calculation by looking at bandwidth. So the higher the bandwidth, the lower the cost. That's basically it. The higher the bandwidth, the lower the cost. So it's going to choose the lower cost path to a destination over a higher path cost to a destination. So let's see what Boson is going to say. Yep, it says OSPF calculates cost based on the bandwidth of an interface. The higher the bandwidth, the lower the cost. So I just explained that. It says when 2 unequal OSPF paths exist to the same destination, the router would choose the OSPF path with the lower cost. And I also explained that. It says to calculate the cost, divide 100 million by the interface bandwidth in bits per second. Thus, a 100 megabit link would have a cost of 1. A 10 megabit link would have a cost of 10, a T1 would have a cost of 64, and a 64 kilobit would have a cost of 1,562. Fast Ethernet and Gigabit Ethernet links by default will have the same cost of 1 because the reference bandwidth of 100 megabits per second. We can change that. We could configure a higher reference bandwidth on each router, so the Fast Ethernet and Gigabit Ethernet links would have different costs. You would definitely want to do that in production networks, so you can use a Gigabit link over a Fast Ethernet link, because Gigabit Ethernet has a higher bandwidth than a Fast Ethernet link. Okay, so now on number 3, it says on router 5, issue the necessary command to modify the OSPF cost of the Fast Ethernet 10 interface to 63. When the network converges, what might you expect to see when the routing table? What might you expect to see in the routing table on router 5? So basically what we're going to do is we're going, for this specific entry right here, we're going to make the cost higher. So we're going to have a cost now. If we implement a cost of 63, this specific next hop will be taken out. So the 203.0.113.26 will no longer be in the routing table. We will only see this route right here, this next hop route to 203.0.113.21, because it is going to have a lower cost. We're basically modifying this one to have a higher cost. So let's go ahead and do that. And once this happens, like I said, we will only see this interface. We can remember Fast Ethernet 1.1. That is going to be the only one in the routing table after we do this. So let's go on to confirm that. Let's do a configure terminal. Let's go into interface configuration mode for Fast Ethernet 1.0. And we want to do an IP OSPF cost of 63. Hit enter there. And we're going to give it some time for the network to converge. So on number 4, it says allow time for the network to converge. Then on router 5, issue the necessary commands to display the routing table. How many paths does router 5 have to the 203.0.113.8/30 network now? How is the cost for these paths calculated? So let's do a end. Let's do a show IP route now. And if we look, we now see that there's only one entry to the 203.0.113.8/30 network. And that is the one that I said would still be in the routing table, which is the connection from the Fast Ethernet 1.1 interface. The one that we previously had, if we go back up, the Fast Ethernet 1.0 is now gone. And that is because we adjusted the metric to 63, which is higher than the metric of 2. So the metric of 2 is now going to be the only one that we see in the routing table, and that is the one that we still see. Okay, so looks good. And it says, how is the cost for these paths calculated? Well, the path for router 5, the original path for this network right here never changed, but the other one did. We manually configured a higher cost for the Fast Ethernet 1.0 interface, and the Fast Ethernet 1.1 interface still has the original cost of 2. All right. So on number 5, it says on router 4, issue the necessary command to raise the OSPF cost of the router's gigabit 0.1 interface to a value of 10. All right, so let's do that. And now when we do this, we will now see that this path right here will have a higher metric as well. It'll probably have a metric of an 11 since we're configuring a value of 10. But let's confirm that. Let's do a configure terminal. Let's go into interface gigabit Ethernet 02. And let's do an IP OSPF cost of 10. Hit enter there. Let's do an end. And now number 6, it says allow time for the network to converge. Then on router 5, issue the necessary command to display the routing table. Has the path to 203.0.113.8/30 network changed? Why or why not? Well, the path will not change. We will still have the same path, which will be the next hop of 203.0.113.21. The metric just will be higher. But the metric for this route is still going to be lower. The next hop, I should say, to this router will be lower than the one that we configured up here, which would be 63. That one will not be added. We would still have the same next hop. It'll just be a higher cost because we just configured the cost to be 10. So we should see it appear as 11 in the routing table. So let's do a show IP route. And if we take a look, so it didn't change. I thought it would change, but it didn't. Let me make sure that I did that correctly. Set the gigabit Ethernet 02. So yeah, I configured the cost. All right, and it says allow time for the network to converge. So yeah, it should be showing as an 11. Maybe it needs a little bit more time for the network to converge. Not sure. Let's try that again. Oh, okay. Well, I'm actually looking at the wrong one, but it still has a metric of 2. So let's try that one more time. Yep, so it's still showing as a metric of 2. Not sure why, but it just may be an error in Boson. But even Boson on its answer that it gives me, it says based on the output, you can determine that R5 still forwards packets for the destination of 203.0.113.8/30 network through the fast Ethernet 1.1 interface, which is directly connected to router 4, which has an IP address of 203.0.113.21. Although both pass through router 2, and the path through router 4 still has the administrative distance of 110, the path through router 4 now has a cost of 11, which is the fast Ethernet 1.1's interface cost of 1 added to the manually configured cost of 10. So that's why I said 11 as well. I think it's just the error in Boson that is just given, that is throwing this error right here, and it's still saying a metric of 2. But all good. We understand what it should be. All right. And it says, however, the OSPF cost of 11 remains lower than the cost path through router 2, which is 64. And we configured that up here when we adjusted the cost to 63. All right. So it says, therefore, router 5 prefers the path through router 4. So before we turn this in, let's make sure that nothing has changed. Yep, so it's still showing the same thing. So I think it's just an error. All good. We understand what we're supposed to see. So it's all good. So that looks to be the end of this lab. So let's go ahead and grade, and hopefully we did everything correctly. And we didn't. So let's see what we did wrong. So yeah, that's the reason why. I definitely inputted this. I definitely inputted. Let me see. Expected running config is supposed to have this, which is what we definitely typed. I'm not sure how it didn't. It didn't register for some reason. Boson sometimes does that. We definitely put that in though. And on router 5. Okay, so I did it on router 4 instead of on router 5. So that's the reason it threw the error. Okay, so I did it on router 4 instead of on router 5. So let's do, let me see. It says I did it on router. Let me do that one more time. So on router 5, it should have a IP OSPF. On router 5, it shouldn't have a, so on router 5, let me go back to router 5. Let me do a configure terminal. Let's do a no IP. Well, let me go into interface configuration mode for gigabit Ethernet 02. Let me do a no IP OSPF of 10. No IP OSPF cost of 10. Let me go to router 4, and let's go into configure terminal, interface for gigabit Ethernet 02. And let's do an IP OSPF cost of 10. Now let's try to turn it in. And yeah, that was the error that it was throwing. So all good. We figured out what was going on, got everything corrected. So I appreciate you guys for watching this one, and I'll see you in the next one.